So we'll talk about what is computer vision. What is computer vision is when we see this particular image, we can identify this particular image as that of a cat. Okay, so any human can identify this particular image as that of a cat. But what a computer sees is when uh, when a machine sees or when we capture this image using a digital camera and read it into a computer, what the machine sees is a set of zeros and ones. It cannot identify this particular image as that of a cat. So what computer vision aims is to bridge this gap between human and machine understanding. That is, human can understand this particular image as that of a cat, and a machine can see only zeros and ones. And from that zeros and ones, the machine should be able to identify that this is an image of a cat. That is our aim of computer vision. Basic aim. Okay. So, some history about computer vision. The first everything started when an image was scanned on a computer. Earlier, the images were not digital images. The first image was scanned into a computer in 1959. Okay, 1959, first image was scanned into a computer. And in 1963, a professor at MIT gave the students a simple problem to solve. And that was the first where AI has emerged as a solution to a computer vision problem. And the first computer vision problems were optical character recognition, like you have a character like 0 to 9 characters, and you'll take a character and then you'll match it with, if you have a zero, you'll match it with your zeros in the database. You'll have a set of images of numbers in your database, and then when you're given a new image, you'll be matching that with the already available data in the database and comparing and finding out which number it is. That was the first computer vision problem that was solved, and it was in 1974. And after that, in 1982, there was some algorithms. Some algorithms were developed to find the edges and corners. That was way back in 1982. There some edges and corner detection were developed, and the first major milestone in computer vision was face recognition. Already, if you have a data set of faces, some available people, you have a data set, and identifying a new person as which person in this particular data set. That was done in 1991 using eigenfaces concept, which used eigenvectors and eigenvalues. PCA was the basic thing used there. So that was in 1991. After that, in 2001, Viola George's face detection was developed. This particular face detection algorithm was used in a mobile phones while taking images. It usually shows a box around the face. So this particular algorithm was used earlier. And in 2012, there was a huge change, and that is when deep learning came into being. Okay. So in 2014, GANs were developed for image generation. So in 1959, first image was scanned into a computer, and by 2014, computers started generating images by their own. So that is the advancement that we are in now. Computers can generate their own images. Okay. So that is where computer vision is right now. So moving on, what makes human distinct is, now we can identify a lot of things. We can, if we have already seen things like we have already seen cat. So when you see another cat, you can identify it as a cat. That is what we have learned from our young ages. So that is a lower form of intelligence. That is, if we have seen something earlier, we can identify it, and that particular thing is called recognition. Okay, so humans can recognize things. So we want the computers to do the same. We want the computers to recognize things like we can do. Okay. And next, what a human can do is human can generate ideas. Okay. For example, I'm not speaking from what I'm not speaking from computer vision prospect, but if some Newton actually put forward the idea of gravity when uh, apple fell on his head. So if somebody here, if somebody a mango falls on the head, he can relate that it is because of gravity. Because apple and mango, even though they are two different things, when it falls down because of gravity. So something we have seen, but we can generate new ideas based on existing facts. That is what is generation. And next, that is also something which makes human different from other living beings. So we want the computers to do the same thing. We want the computers to generate ideas. We want the computers to generate images. We want the computers to generate something from little bit they have seen. Okay, generate new ideas from what they have seen. And finally, human can create. Human can draw pictures of those things that they have never seen. And human can write stories, write of imagine things and write stories. They can create new ways. That is another the most higher form of intelligence. They have not seen something, but they can imagine things and they can create. So creativity is the higher form of intelligence. And finally, computer vision researchers want the computers to do the same. So now currently, computer vision has got good results in this recognition category, and generation also a little bit of work is being done, and creation started with creation. Okay, computer vision researchers have really started with creation. So this, what I said was main. A human, what makes a human distinct from other living beings is that a human can recognize things, a human can generate new ideas from what they already know, and also human can create a totally new thing. So this is a this is what the computer vision researchers also want the computers to do. So we are moving, the computer vision researchers are moving from a lower form of intelligence to higher form of intelligence. They want the computers to move from a lower form of intelligence to a higher form of intelligence. So that is what is happening in the computer vision world now. And so I thought I'd review a few things happening, what a few things happening in recognition, a few things happening in generation area, and a few things happening in create creation area. So okay, recognition. Recognition is first thing what was done in computer vision recognition was image classification. You will be given a trimmed image of a particular object. For example, trimmed image of an aeroplane, automobile, bird, cat, etc. And you need to identify which particular image, or you want the computer to identify which particular image is that in that particular picture. So that is what was done first. Okay, earlier this was done using 10 object classes. There were 10 object classes like aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So there were 10 object classes, and each object class, for each object class, there were 5,000 images, training images. And from this training images, a model was trained and it was tested on a 10,000 test images, which contained 1,000 images of each category. And the accuracy obtained for that particular data set was called CIFAR 10 dataset, and the accuracy was 99.5. Even humans cannot identify those images with such big accuracy, okay, such a high accuracy. So computers could achieve on that particular data set, computers could achieve an accuracy more than what human could achieve. So that was about CIFAR 10 data set. But then that particular task was that particular task of classifying 10 object classes was saturated. So what happened is people started developing another data sets which contain more object classes and more data. So always more data is good for a machine learning algorithm. So they started generating data sets having more object classes. And another latest used object data set is called ImageNet. ImageNet has, in place of 10 object classes in CIFAR 10, ImageNet has 1,000 object classes. And even on that ImageNet data set, the accuracy of 90.88% was obtained. So image classification is a very researched area. Still there are issues, but it is moving on to a very large number of object classes. And occluded images, if the object is occluded, even a part of it is occluded, we can identify. So the researchers want to make computers do the same. So that is what is happening in image classification area. So next thing was next level of recognition is called object detection. Earlier we were given an image containing only that particular picture. If it is a car like this, the car will be contained in the whole image. There will be only car, there won't be any other objects. So you have to identify if it contains a car or not. So, but in object detection, we want, if suppose in this particular picture, sorry, 1 minute. Okay. So if in suppose in this particular picture, I want to identify the persons in the image. Okay, so people in the image. I want to identify the people, and I train a detection algorithm. And what object detection does is it spatially localizes that particular object class. Okay, object detection spatially localizes that particular object class. So it'll draw a boundary around that particular object class of interest. Suppose in this particular picture, our object class of interest is person. So it will identify the person and draws a bounding box around that person. That is what is called a simple object detection task. And next, a little more advanced task is called semantic segmentation. In this particular task, each pixel is identified as whether it belongs to a person. Here, just a bounding box was drawn, and in this, each pixel is identified as whether it belongs to a person or not. So each pixel is identified as whether it belongs to a person or not. A still more advanced version is instance segmentation, where if we have five person, each pixel is identified as belonging to person 1, person 2, person 3, person 4, or person 5. So this is object detection. And this particular thing is used in not with just simple images. We can apply recognition in medical images also. For example, if we have an OCT image, OCT image is a particular image of eye, and if we have that OCT image, we can use it to identify particular diseases. So we can use this particular computer vision algorithms in medical images also, and it can be used to identify different diseases. Similarly, uh, as we have done in the case of object detection, here also, if there are images of tumors, it can be used to segment the tumors also. So that is about image classification and segmentation in medical images. So the same computer vision algorithms that are developed for normal images can be modified to be applied in image classification, in medical image classification and segmentation also. So another very fast developed research was in identification of COVID from different types of medical images. It was very fast. For example, there were works identifying the level of COVID infection from chest X-rays without the intervention of a very expert doctor. So just a radiologist was enough. And then CT scans also, if that can be properly identified. There were works on identifying the infection from CT scans also. So that was another area where there was a lot of works in very short span. And so we have talked about images, image classification and object detection in images. But another vastly researched area is video understanding. So we know what is happening in a image, but we need to know what is there in an image, but we need to know what is happening in a video. If the computer has to understand totally as we understand a scene, we want the computer to identify what is happening. For example, if there is a camera placed in a surveillance, for a surveillance application, we want to know if there is a person there or not. Also, we want to know what that person is doing in that particular image. We want to know if he is running or walking normally or something terrible has happened. So we want to know what is happening in the video. So that is another area which is often researched. And the first, like image classification, in case of videos, there is large scale activity recognition. There are a large number of activity data sets. For example, a lot of activities like dancing, cooking, etc. will be there in a trimmed video, and the task of machine is to identify what is happening in that particular video. So it involves labeling a large number of classes of actions using machine learning models. So that was one area, and like it is used in automated surveillance. We use this particular thing in automated surveillance, and we use it to analyze what is happening in a crowd, and also we used it for video searches and for human computer interaction. And another very important application is wearable devices. This particular thing is used in wearable devices also. Another some other task in computer, this video understanding, which are researched is, the first one is dense captioning. Dense captioning means for each, like we have seen the subtitles in a movie, and for each frame, there'll be a sentence generated, like what is happening in that particular frame. Okay, so that is what is called dense captioning. And next is spatial temporal localization of action. Earlier, just the computer identifies whether that action is there or not. And in spatio-temporal localization, the computer will identify where a particular action is taking place. For example, if it is writing that we have to identify, the computer will identify where this particular writing is taking place, and it will draw a bounding box around that particular action. Okay, so that is what is meant by spatio-temporal localization. And there is also a temporal action localization. Instead of spatial localization, it will just temporally, it will identify the frames where a particular thing is happening, particular action is happening. Okay, so that is recognition. And also another thing, another important application is abnormal event detection. For example, in surveillance videos, there'll be normal actions will be the most prominent ones. Usually, there'll be normal actions. Like if there is a surveillance camera, most probably there won't be anything abnormal. But some cases there might be a robbery, or there might be some attack, or there might be some people fighting. but the probability of those actions will be very less. So in abnormal event detection is therefore treated as a special case of video understanding. And in this particular thing, computer will learn the normal patterns. Normally, what will happen? And when something abnormal happens, it will be able to identify that this is not normal, but it can't identify what is happening, but it can identify this is not normal. So that is what is abnormal event detection. And this particular abnormal event detection is also used in medical anomaly detection. In this also, a computer can learn the normal patterns, the normal scans, how would the normal scans look, and to compare that normal patterns to abnormal, and if there is any deviation, it can identify this particular thing is abnormal, something is abnormal in this particular image. That is what medical anomaly detection means. And that was recognition. So we talked about the first level of intelligence, recognition. In recognition, image classification was done, and detection, object detection was done, and also video understanding was there. And all these things can be applied to medical images also. Okay. So that was recognition. And next is then what happened is then the computer vision researchers were very impatient, and they wanted the computers to generate images on their own. Okay. From just giving a noise, computer vision researchers wanted the computer to generate faces. Well, that was what was done using GANs, or generative adversarial networks. A set of computer was trained to on a set of face data, and then when a noise was given, it was supposed to generate a face image that it has never seen, and the person doesn't exist. So that was first thing that computers do in the generation part. And then next was we'll give some attributes, like I want the person or the image to have a glass, some spectacles, or I want the image of a child, so that I can give an image of a child and I'll get an image of the child. Or I can give the image of a person looking in some different poses. Okay, so that is what that was another step. I want this particular, I want an image like this. So, or I want a hairstyle like this. That is what was done in this style GAN. Okay, a style was copied, a style from the input images. These are the input images, and these are the first row and first column are the input images, and these are the outputs produced by the style GAN, copying the styles from the input image. Okay, so those are that was the next level. Okay, first it just started generating some random faces, and then uh, uh, it started generating faces according to the style we gave. Okay, new faces, totally new faces according to the style that we gave. So that was another development. And then generators had other applications, like if we have a low resolution image, it can be converted to a high resolution using generators. So that was another application. And if we have a haze removal, same generator was given, used to do haze removals also. So these, and then final level of human intelligence is creativity. And computer vision researchers want the machine to be creative. So earlier, we have seen that when a video was given, computers could generate a caption. Okay, when a video was given, computers could generate a caption, and that was just recognition. So it will recognize what is happening in the video and it will generate a text. That was recognition. But creativity is when I'm giving a text image, I'm giving a story, and the GAN will be generating some images based on that, or a cartoon based on that particular story. That is one of the first works in creativity. That is, you give a caption or you give a text, and based on that text the computer will generate a image. Okay. And another is artworks by Gann. There are modern art by Gann, and that was also creativity uh, level of intelligence. So these are the main category of research happening in computer vision. If you are going to start, or if you want the students to explore, if you want your BTech or MTech students to explore, you can start with either any of these works. Okay. And next is some other computer vision researchers. Some other computer vision researchers include, first one is 3D reconstruction. When you're given you a 2D image, you're just given an image and you need to recover the 3D properties from that image. That is what is called 3D reconstruction. And then 3D reconstruction can be done from single images. Different shade and textures of a single image can be used for 3D reconstruction. Then multiple cameras or 2D two images. We usually see using two eyes, and we can identify the depth properties. We can identify, a human can identify the depth properties. Similarly, using two cameras or two images, a 3D reconstruction or the structure can be reconstructed. That is called stereo vision. And next is, from multiple images, structure of an object can be identified, and that is called structure from motion. And these are the prominently researched areas. And these are also used in medical imaging. As I've said earlier, all these algorithms are adopted into medical imaging also. These are examples of using 3D reconstruction. The why doctors have used a 3D model for kidney operation, and also 3D technology was used to reconstruct a man's skull. Okay. And 3D reconstruction is also used to model the structure of protein to study the structures in detail. Another 3D reconstruction includes simultaneous localization and mapping, which is called SLAM. It is used to, a robot will be navigating in a particular environment, and then we'll be mapping build a map of that particular environment where no robot is in. That is what is called SLAM. And another currently most researched area is called edge revolution or embedded vision. All the computer vision algorithms that we develop are using heavy computations. Now we are using a very large deep learning networks, and all those networks take a lot of computational power. But finally, where this has to be used is, we have to use this particular algorithms in a mobile camera or in a surveillance camera or in a automated driving self-driving car. So we can't have a very large computer or a very large GPU which consumes a lot of power inside these devices. So what we need is, we need to do the processing. The first thing we need is, the processing should be run in real time. And next we need is, we need very small computing devices, and also we need these devices to consume very less power, because all these applications involve either a wearable device or some mobile platforms. So we need these devices to consume very less power. So that is what is happening in embedded vision or edge revolution. We want this to consume very less power, so we want to optimize our algorithm. Okay, so there two types of research is done. Even developing a specialized hardware is also done, and also optimization of already existing algorithms is also done in embedded vision. That is a very prominent area which can be very can be researched. Okay. So optimizing algorithms usually involve choosing right architecture and setting some weights. You'll have a lot of weights. Even if we set some weights in random, it won't affect. So setting some weights to zero and then quantizing the weights to lower bits. That are some things that can be done to optimize or the algorithm. And another recent development was explainable AI. Okay, so when earlier when an image of a cat was given to a deep learning algorithm, it will finally output it that it is a cat. What happens inside the deep learning algorithm is not known, or why did that particular machine learning algorithm identify this particular image as that of a cat? That is not known. So explain why did you do that. Computer vision researchers want the computer to explain why this happened. So that is another area which is most commonly researched. Okay. Uh, then there are learning from minimum number of data, and also we don't need to see a lot of cat images to identify that this particular thing is a cat. Just one would be enough. So uh, that is something the computer vision researchers want. Computers also know. Computers should also learn from minimum number of data. That is what is called single shot and zero shot recognition. And when the computer started generating a lot of images, there was another issue. When the computer started generating images, there was the issue of uh, uh, generating fake images. For example, there are a lot of videos that were generated, which were fake and which were very generated to be misused. So identifying fake images and identifying the original images is another important area which is currently researched. So we can pick either any of this area to start with a computer vision research. So I'd be dealing with the previous methods. Like earlier, you have already learned about. I think during the first session, I think there was a session about using deep learning for image recognition or classification. So you are already familiar with deep learning. Today, I'll be talking about the previous methods where people used to extract handcrafted features and train a normal machine learning algorithm to develop for detection or classification. So again, we can identify, seeing this image, we can identify this image as that of a dog, and what human can recognize this image as that of a dog, and what when you read this to a MATLAB or a Python software, what you can see is a set of numbers, and machine sees is a set of, so what machine sees is a set of numbers, and from this numbers computer has to identify that this is the image of a dog. So that is what compu- uh, computer vision researchers want computers to do. So, why do you want machines to identify in the first place? Because there is a lot of data, and it is hard for human to keep track of this data. Okay, so there is a lot of data. There are a lot of surveillance cameras, even in Trivandrum city in and around. There is a lot of surveillance cameras, and it is hard for human to keep track of what is happening in this particular camera. And there are a lot of social media, and there are a lot of images, videos, and other text data generated. So it is hard to keep track. So it is better if machines can identify. So can you identify some computer vision architectures which use, can you identify some computer vision architectures that we use in our day-to-day life? Can you give me some examples? You can type in the chat box if possible. Can you identify some computer vision applications that we use in that we see in our day-to-day life? Okay, so let me show. So the first computer vision algorithm that we usually use is a camera, and most of the mobile phones have a face detection algorithm, which shows a bounding box around the face. Okay, so face detection is a computer vision algorithm application that we use. And then you have the Google Lens. I think most of you should have used the Google Lens. We can use Google Lens to scan an image or for text or something. You can do image search using Google Lens, or you can extract the text from an image using Google Lens. So Google Lens is something which you use day to day. And then there are image search engines that we use. And then we have AI cameras installed in our city, or AI cameras installed in Kerala. So we have traffic and surveillance, and then we have recommendation systems like when we search something, search some images or videos, we'll get similar recommendations. So we have the recommendation systems. Those are the day-to-day computer vision applications that we use. And what is the difference between traditional programming and machine learning? In traditional programming, for example, if I want to check if a given number is odd or even, I can use a rule-based algorithm, or I can hard code an algorithm. I can, if I am given a number, I can divide it by 2, and if there is a remainder, it will be odd, and if there is no remainder, if the remainder is 0, if the remainder is 0, then the number is even. So I can hard code the algorithm, and I can write a program. So that is traditional programming. But what computer vision task is, we have to, from this particular image, we have to identify the dog. And there is no hard code, there is no rule regarding, I can say that the dog has 2 ears, uh, tail or something, but there is no way to hard code to identify all these different algorithms, all these different images of dogs. So we need machine learning. So there is no way to hard code. So what we do is we'll use all the data. We'll have a lot of data. We'll collect that data. We'll use that data to we'll use that data to train a machine learning model, and then we'll make it identify. We'll give a lot of dog images to the machine learning model, and then we'll say it is that of a dog. And finally, the machine learning model, by some iterations, learn something, and then we'll give a set of cat images, and we'll say that it is a cat. And so machine learning algorithm learns something, and finally when we give a test data which the algorithm hasn't seen before, it will be able to identify. So that is why how the machine learning algorithm works. So how does this machines identify? When I'm given a cat image, I have to first do is I have to extract some handcrafted features. I have to extract some features which makes this particular image distinct. Okay, I have to extract some handcrafted features, and then I have to train a machine learning algorithm to identify that, or to give an output that this is a cat. Okay. And this was classification using handcrafted features. And later, this handcrafted features was replaced by deep learning algorithms, where data is used to train the feature part also. Features are also not extracted by a person, or not engineered by a person. Instead, the algorithm learns the important features from the data also. That is what happens. In addition to just classification, the algorithm learns the feature extraction part also from the mm, uh, data. So we'll be focusing on handcrafted feature extraction. I'll give some introduction to handcrafted feature extraction and some just some important machine learning, just introduction to machine learning algorithms also. So before starting with this, I can think we can have a break of 10 minutes. 10 or 20 minutes is okay. Yeah, video tracking is a good thing. So can we break for now?
Okay, miss.
Okay. We'll join by 8:05 or something. 8:05.
Okay. Dear participants, we will be having a break for 10 minutes. We can join back at 8:05.
Okay, dear participants, please join back so that we can continue. Anitha ma'am, please continue with the section.
Okay. Now let us start. Hope the screen is visible and my sound is clear. Is the PPT visible?
Yes, ma'am.
Okay, thank you. As I have told you earlier, how machines identify from image, how do machines identify is machines will extract some kind of handcrafted features engineered by a computer vision researcher, and then we'll use those features to train a machine learning algorithm, and then the algorithm will identify the particular image. First we'll see about features. Or if we are giving an image like this, we can't identify the image of a cat by just looking at the numbers. We can read this image as a set of numbers or a matrix, and we can't identify that it is a cat from those set of numbers, because if the cat is a bit shifted by position, the numbers will be totally different. Or the image is little bit brighter, the numbers again will be totally different. Or it is darker, the image if of same object, the image will be totally different. So we can use the image intensity values to identify what object is in that image. So what we can do is we can extract some distribute distinctive attributes or some description of something that we want to label or differentiate, and these are called features. And the most commonly used local image features are edges and corners. So we'll see how to identify the edges first. So we have a image like this, and after extracting the edge, you will get something like this. And this is another image, and edge detection will give you this image. Okay. So how do you, what is an edges? Edge is the border between two regions in an image. For example, this is the background and this is the object of interest. So it is the border, edge is the border between two regions in the image. Or it is the change in image intensity. Here we have black color, so the intensity of the image is different, and here we have a little lighter color, so the image intensity is different. So where does that change takes place? That change is called the edge. Or where does this change? This is gray and this is brown. Where does the change take place? That is edge. So you have an image intensity and you are representing the image intensity as a function of x and y coordinate. X and y coordinate is spatial coordinates, and you are representing image intensity as a function of x and y coordinates. And what is the mathematical operation to detect change in intensity? uh, can someone reply, like, what is the mathematical operation that can be used to detect a change? uh, The mathematical operation that we usually use to detect a change is differentiation. Similarly, here also we can use differentiation to detect the change in image intensity. But we have to do differentiation in, we need to know the change in x direction and we need to know the change in y direction. So we can use gradient operation, that is in differentiation in x direction, differentiation of the image intensity in x direction and differentiation of the image intensity in y direction. That is what it is called, gradient. And we can use this gradient to identify the edges in the image. So to identify the edges or gradient, simple operation we can use is usually derivatives are defined for continuous functions, but image is not a continuous function. Differentiation for an image can be approximated that as differentiation at point xy is equal to intensity at point x plus 1 minus f of xy, and similarly differentiation in y can be approximated like this. So we can use this gradient operation to detect the edges, and this is the first derivative operation, and magnitude of this gradient can be taken to identify the location of the edges, and direction of this gradient can be taken to identify in which direction there is change. Okay, so that is how a major important feature called edges obtained. Also, the edges can be obtained using second derivatives also, or it is a special operation called a Laplacian operation, which is second derivative with respect to x and second derivative with respect to y. Both are summed together, and this can also be used to identify the edges. This particular operator is usually used to identify the edges. There are other operators as well. Okay, and from this operators, we can find a kernel. To represent this particular operation, we can find a kernel. Kernel is like the impulse response of a system, and this kernel can be convolved with an image. You have already had a session about deep learning, so I think convolution operation should be familiar. If it is not familiar, the convolution operation is you'll have a kernel, and you can move this kernel over the image, and you can multiply each pixel with the kernel value, and this particular pixel, the operation of the kernel at this particular pixel is multiply the value of this kernel with neighboring pixels, and take the sum and then replace the value. So applying this particular kernel to this particular image, you will multiply each neighboring point using this kernel and sum, and then replace this particular pixel. So that is how convolution operation during using a kernel is done. Then this kernel is shifted, and again the operation is repeated to replace each pixel. Okay, so that is how convolution is done. So using edge, there are a number of edge detection kernels, and using those kernels you can find the edges. And there are a lot of edge detection algorithms like Laplacian of Gaussian, difference of Gaussian, canny edge detector, etc. So this edge detection algorithms have three stages. The first stage is there will be some noise. You have to remove that noise. So you'll use filtering, and then you will be using this differentiation operation. This differentiation operation can be any approximation. It can be a first derivative, it can be a second derivative like Laplacian, or it can be some other edge detection differentiation approximation algorithms like Sobel operator, etc. And once the edges are detected, once the differentiation is done, you will get an image, and finally from that image you have to detect the edges using some thresholding. So that is what is the edge detection algorithms usually do. This is an example which I have done. This is an image, and an LOG is applied, or Gaussian filtering is applied to remove the noise, and then Laplacian is applied. So once the Laplacian is applied, you will get an image like this, and this image is thresholded to identify the edges. So this is the result of the edge detection algorithm. And then even though edges are very good features, there are an important computer vision application is called image matching. For example, this is the image of the same mountain peak, and I have to identify that both are same. Just the difference is that these images are taken from a different angle. Also, this is the image of the same house, but I have to identify that both are same. So here, instead of using edges, A more prominent feature would be a corner. For example, if I'm taking a patch like this, if I'm taking a patch like this in the first image, then I have to identify if this patch is there in somewhere here. So this patch is here. It can be matched to some place here. So there is no information in that patch. So it is not a good feature. And next is I can take an edge like this. This is an edge. I can take an edge like this. I can try to match this edge in somewhere here. But when I try to match, it can be here, here, or here. It can be in either place or it can be some other edges. So a more promising feature would be a corner like this. A promising feature would be a corner like this. There won't be many corners similar to this. So for corners are easier to match than edges, and they are more promising features, or they are called good features. For example, in an image like this, if I'm taking a patch like this, I can match it to anywhere here. But if I'm taking a patch like this is a corner. I can match only to this particular point. So that is the advantage of corners. So corners are better features than edges. So corners are unique and distinctive, and they are not global and not specific. But for example, take a image, and this yellow is my original image, and I have taken another shifted image. This red one represents the shifted image, and there is a if I'm taking a patch like this, if I'm taking a patch like this in the third figure, I won't be able to match it anywhere. I'm taking the first figure, yellow figure, and I'm taking a patch like this in the yellow figure, and I'm trying to check if it is there in this red one, and I won't be able to match in a proper position. Even then, next I'm taking a patch like this. If I'm taking a patch like this, I can match it to like this in the yellow figure. I can match it to this red one, this red one, or this red one. I can have a number of red positions where I can match. So that is also not a good feature. Instead, a good feature would be a corner which I can match uniquely. So corners are better features. And the basic idea is there was a corner detector. I said earlier, a corner detector was developed, and the basic corner detector that was developed is called Harris corner detector. And the basic idea of that corner detector is uh, in a flat region. In a flat region, if you take a flat region, there won't be any change in any direction. There won't be a change in intensity in any direction. But if you take an edge, there will be change in the direction. There will not be any change in the direction of the edge. If we take this particular direction, there won't be any change. It is black here. But if you take a direction perpendicular to the edge, there will be change. It will changing from white to black. So edges have a change in one direction. But when you take a corner, there is significant change in every direction, significant change of intensity of image in every direction. So that is the basic idea that is used for corner detection. And I'm not going into the mathematical details, but using the image, Harris matrix, using the image, the derivatives of the image are computed. Fx of xy is the x derivative, fy of xy is the y derivative with respect to y, and those derivatives are computed, and this particular matrix is formed. And this matrix is the eigenvalues of this particular matrix is computed, and those eigenvalues of the matrix are used to detect the corners. And if both the eigenvalues of that matrix are small, it will be really eigenvalues represent the data spread, how much the data is spread. If both the eigenvalues are small, it represents that the data is not much spread. So it doesn't have much information. It is a flat region. And if the eigenvalues, one of the eigenvalue is large and the other is small, it shows that the data spread is in one direction. So it represents a edge. And if both the eigenvalues are large, it shows represents a corner. So computing the eigenvalues and checking them will help to detect corners. But computing eigenvalues is computationally expensive. So if you want to do a real-time computation, instead of eigenvalues, I can use another score. It was introduced by Harris. So it is the determinant of this particular matrix. Okay, determinant of this particular matrix minus k into trace square of this matrix. K is a experimentally fixed constant. So determinant will give the product of eigenvalues and trace will give the sum of eigenvalues. So it is like a representation. It is similar to comparing the eigenvalues, just a score based on the eigenvalues, but it is easier to compute. So compute using that, if that r is greater than 0, you can identify it as a corner. And if r is less than 0, then it will be an edge. And if r is nearly equal to 0, it will be a flat region. So that is how the corner detector works. Uh, so once we have, so I can have edges. Okay, I can have features like edges from an image. I can find features like corners from the image using this algorithms. And once I have this edges and corners, can I identify that this belongs, for example, if I want to compare these two images, this image is that of a toy truck and this is that of the same toy truck in another angle, placed in another angle. So can I, using corners and edges, can I identify if those are same? Okay, for example, if I'm extracting a corner like this and I'm extracting the same corner, if I compare just the image intensities of the same corner, it won't be same because this is placed in some other manner and this is placed in another, it is rotated. So the image intensities won't be same. So even though you have extracted features, it won't be enough to represent the information in the image. So once you have extracted edges and corners, you need something else which is invariant to this rotation and other transformations so that you can use it to compare and say that these images are same. So those kind of features are called those kind of numbers are called feature descriptors. And a most popular feature descriptor is called scale invariant feature transform. Okay, so as I've said, you can extract edges, you can extract corners. They have a lot of information. They are good features, and corners are most prominent features. But even those are not enough to make a computer identify that these two images are same or to classify an image. So further, what we need is we need something to describe that particular point or particular corner. You can't use image intensities because it will differ if the same image is taken using different lighting conditions. It will differ. So we can use image intensities. We won't be able to compare the image intensity at that corner. So what we can do is we can extract some kind of descriptors based on the neighborhood, which will be invariant to scale. Scale is like even though it is here the truck seems to be larger than this, so invariant to scale and intensity and rotation. So we'll have to find some feature like that. And Swift is one of the most prominent features. It was the most cited paper in computer vision for some time back. I don't know about it now, but SIFT was introduced by David Loeb in 2004, and it was one of the most cited papers in computer vision. It is also a patented feature descriptor. So And shift is invariant to change in same figure. If there is illumination variation, shift points will be same. Shift descriptor will be same. Even shift is invariant to change in viewpoint, and also it is invariant to noise and other transformations. So shift is usually computed by, I'm not going into the details, but there are a specific set of steps to compute this feature. We'll compute a key point. Key point is something like a corner. Key point is something like a corner. And for each key point, we'll find a key point descriptor. We'll find a set of values or a vector to describe the particular key point. And this particular descriptor can be used to compare if the two images are same, or this particular descriptor or this particular vector can be given to a machine learning model to identify the, it can be given to a machine learning model for learning and further classification task or something. Okay, similar to SIFT, there is another descriptor or feature called histogram of oriented gradients. So this is also similar to SIFT. It is also a set of vectors that can be used to represent an image, and this set of vectors can be given to a machine learning model to identify a particular, for example, we have talked about the classification of cats and dogs. You are given a set of images of cats and dogs, and you have to identify whether it is a particular image is that of a cat or a dog. So what you can do is you can extract the histogram of gradients, and then you can form a vector. It will be a set of numbers, and you can form a vector for each image, and then you can give this vector to a machine learning model, and the machine learning model can be used to identify if it is that of a cat, or it can be trained to identify the cat and dogs. Okay. So that is about features. So I've talked about edges, how you can extract the edges. I have not gone into the details of the mathematics, but there are algorithms to extract the edges, and there are algorithms to extract corners, and there are algorithms to describe these features. Okay. So there are a number of algorithms. I've just talked about some example. So once this handcrafted features are extracted, we have to use machine learning algorithms to do our task. Machine learning algorithms to learn from this handcrafted features. So we'll see some prominent machine learning algorithms. And first, when we want to do a cat dog classification, what we have to do is, suppose we want to develop a machine learning algorithm to classify cats and dogs. You're given a image of a cat or dog. You want your computer to identify whether it is that of a cat or dog. So first thing you have to do is to create a data set containing images of cats and dogs. You have to collect a lot of pictures of cats and dogs. So this is an example of a data set of this are cats and these are dogs. And this is an example of a data set without label. Label means I'm saying that this is the image of a cat, this is the image of a dog. So with each image there is an additional information that this is the image of a cat or this is the image of a dog. So we can form a data set first. Okay, then once you have formed the data set, you can extract, you can divide the data set into train set, test set, and validation set. Train set is what is used to teach the machine learning algorithm. We'll use the train set to teach the machine learning algorithm. And test set is something which is used to test our machine learning. How well does our machine learning algorithm works? So that is done using test set. And in validation set, we'll have to adjust some parameters for the machine learning algorithm to learn better. So that was done using a validation test set. So first thing you have to do is you have to collect, according to your requirement, you have to collect a data set, and then you have to divide the data set into test set, train set, and validation set. But if it is the most commonly researched problem, then you have a lot of data sets available, standard data sets available. And the advantage of using standard data set is that you can easily compare your results with the already existing results in the paper. For example, you can download, if you're doing a object detection or object classification problem, image classification problem, you can download the CIFAR 10 data set. It will have a lot of images. There are works which have used CIFAR 10 data set before. So you have done some algorithm and you want to compare your algorithm performance with others, then it is easy because already people have worked on it and reported the results. So it is always easy. If there is a standard data set, it is always easy to work with a standard data set. If it is not available, or you are concentrating on some specific problems related to your area or something, then you have to create a data set and divide it into train, test, and validation data. And once a data set is created, you can take the train data and then you can extract the features. Okay. Features like which you feel important is for your data. Okay. Features, any feature which you feel important, existing features or features which you feel is important for your data. Suppose that my feature vector is a two-dimensional feature. Just it has two numbers, just two numbers. The first one is feature 1 and second one is feature 2. And so what I can do is I have a feature of two dimension, and this blue one I've plotted it in a paper. I've taken the values and plotted it in a paper, and this blue ones belong to that of dog, and red features belong to that of cat. So what I can make my machine learning algorithm learn is, I can make the machine learning algorithm learn the distinction between these two data. I can make the machine learning algorithm learn the distinction between these two data. And once when I get a new data like this yellow one, this yellow one is called test data. I can make the machine learning algorithm classify it as a dog or cat. Okay. So that is classification problem. And the classification problem can be supervised or unsupervised. I have said that the data set can have a label or not have a label. So it can be supervised or unsupervised. So this is the example where you're given features and you're told that this belongs to dog and this belongs to cat. And in this, you're not told whether it belongs to cat, it looks, or there is no label associated with the data. Input data only. Okay. So in this, we'll be concentrating on supervised classification. And in supervised classification also, there are two types of models: discriminative model and generative model for classification. Suppose you have two-dimensional features and features of two classes, class 1 and class 2. And discriminative models, it finds a decision boundary between the two classes. It finds a decision boundary between the two classes. And the example is support vector machine. And generative model finds a data distribution or the probability distribution of each class, so that when a new data comes, it can identify whether it was generated by this probability distribution or this probability distribution. An example for generative model is naive Bayes classifier. So I'll just go through the basic idea. I won't go through the great heavy maths. I'll go through the basic idea of the two classifiers and then introduce you to the computer vision resources and then conclude. Okay. So naive Bayes classifier, the basic idea is it uses probability. Fine, you have to, naive Bayes classifier is a generative model. So you have to model a probability distribution. I'm not going into the details, but just the basic idea of the naive Bayes classifier. So suppose this is not a computer vision data set, but it is prominent data set which is used to teach the machine learning algorithms. It is called a golf data set. Golf data set contains data regarding whether a person played golf on 14 days, and we have to predict whether he'll play golf on the 15th day. So I assume that I'm given just the information about day 1, day 2, and up to day 14, and I'm given whether he has played or not played golf. Okay, so on the 15th day, I have to find on the 15th day would he play golf. So I can use probability. So probability is number of favorable outcomes by total number of outcomes. So here the total number of outcomes is 14, and what is the probability that the person plays on the 15th day is out of 14 there were 9 yes. On 9 days he played. So the probability is 9 by 14, and about no out of 14 he did not play for 5 days, so that probability is 5 by 14. So I have probability of yes is 9 by 14 and probability of no is 5 by 14. So probability of yes is greater, so we'll play. Okay, so that is my first assumption. And next, I'm considering that earlier just the day and whether he played information was just given. But next, an additional feature, this is what is called feature. Additional feature regarding the day was also given. Instead of just output, I'm given an additional feature like how was the day? Was it overcast? Was it cloudy? Or was it rainy? Or was it sunny? So in addition to the original whether he played or not or output, another feature about the day was also given. And if that is given, I can use conditional probability. I can use the condition, how the I can condition this probability of playing on what kind of day it was. So what is the probability I have on day 15? I'm given that it is a sunny day. So what is the probability that the person will play golf on day 15 if it is a sunny day? So let's see how we can use probabilities. Okay. I have to find the probability that it is a sunny day. 15th day is a sunny day. So what is the probability that the person will play golf? So I can use conditional probability, and I'm not going since the time is less. So it is a sunny day. What is the probability that he'll play? Yes. So out of total sunny days, there are total of 5 sunny days, and out of 5 sunny days, the probability that he played on 2 days. So the probability is 2 by 5. Given sunny day, he'll play is 2 by 5. And given sunny day, he will not play is there were 3 cases when he did not play on a sunny day. So given sunny day, he'll play is 3 by 5. Okay, so probability of given sunny day, the probability that he'll play is 0.4, and probability that he'll not play is 0.6. So since it is a sunny day, instead of playing golf outside, he can sit home and watch TV. So that before this particular information that about the day was given, our assumption was totally wrong. So features are very important in classifying. This is how probability or conditional probability can be used for learning from data and to model. Similarly, if a number of features about the day, like the day is, the temperature, the humidity, and wind is given, we can classify the data. That is where Bayes' theorem comes in. I'm not going into the details. Anyway, there are a lot of assumptions when this number of features come in. Anyway, this is the basic idea of a Bayes classifier. Bayes classifier uses probabilities to model the two different classes. I'm skipping this too. So that is about the generative model. I'll get 10 minutes, so I'll go on to support vector machine. The basic idea of support vector machine is similar to earlier case. You will have I'm having, suppose I'm having a two-dimensional data of two classes, and I have plotted this two-dimensional data. And support vector machine uses decision boundaries for classification. It will find a line that separates the two classes, and I can have different types of lines that separate the two classes. Out of these three sets, the first one is, sorry, 1 minute. I'm sorry. Out of this three, I can find infinite number of decision boundaries. But out of this three, which do you think will be a better decision boundary? It will be difficult to identify from this picture, but if I draw something like this, I'm drawing a line parallel to this decision boundary through nearest data point, and I'm drawing lines parallel to decision boundary through nearest data points in both classes, and then which would be the best one. You can see that here the margin is wider. Here the difference between the distinction between the two data points, this belongs to the one class and this belongs to other class, and here the margin is wider, so this would be a better data point. No, sorry, better decision boundary. So basic idea of SVM is to find out the decision boundary with the widest margin. And these points which are on the margin are called support vectors. We can use this point to find the widest margin. I'm skipping the mathematics on how to find the widest margin. Another important term, or then another important thing in support SVM or support vector machine is the use of kernels. For example, if we have a feature like this, I have a two-dimensional feature, and this blue belongs to one class and red belongs to another class. I can separate these two classes using a single decision boundary. So what I can do is I can convert it to another domain, or if it is a I can take, if I take the square, if we consider this as a quadrant, this is the negative, I can consider the square of this so that the entire points will be moved to the first quadrant. Then it will look something like this, and then I can separate. So this is the basic idea of kernel in support vector machine or kernel in SVM. You will convert it to another domain using kernels where the data will be separable. Instead of just features, we will convert to another domain. Okay, so those are the basic things in support vector machines. Sorry, machine learning. I wanted to talk about naive Bayes and support vector machine, and next is anomaly detection. I wanted to show you an example, but I am skipping this for now. So the major, if you want to start a research or if you want some project in computer vision, the major publications that you could refer is, there are very important conferences where latest work will be published. You shouldn't go for any simple conferences. These are the most prominent conferences where latest work in computer vision are published. One is called CVPR. Another one is ICCV, and also there is a journal on pattern analysis and machine intelligence, and this journal by Springer on IJCV, International Journal of Computer Vision. And these are the things where you can have very good quality publications, and you can refer that and start your work. Most of the papers will have shared code. You can download that code and start, and then you can proceed from there. And these two are Indian conferences, the most prominent Indian conferences in computer vision. Uh, another method where how you can start is in associated with this computer vision conferences, there will be a number of challenges where they'll give a computer vision problem, and they'll also give a computer vision data set, and they'll ask people to upload the solutions. So you can make your interested students participate in these challenges if possible. There are challenges associated with all these conferences, including this Indian version of the conferences also. There are challenges associated. So the advantage of challenges is you will get a problem. You just have to choose a problem from a list of work challenges. And another thing is they'll give you the data set as well. So participating will be a good experience, even though you won't, if you are not top also, participating would be a nice experience. Computer vision resources, there is a site called CV Foundation, Computer Vision Foundation. You have all the computer vision conference papers in this particular site. And there are computer vision books on by Celesky. This is a very good book to read. And then there are other books like this one. And there are a lot of videos and courses. And this course by this one is deep learning based course, CS231N by Stanford. And this is from Berkeley by Jitendra Malik. It has a lot of interesting PPTs, and this course is very simple and has a lot of a number of videos available in YouTube. So with this, I think I'll stop. If there are any questions, I can take the questions.
Participants, if you have any questions, please share.
Good evening, ma'am.
Yeah.
Hi, ma'am. So I had a question. So you have mentioned clearly on the corner detection in detail, that how you do the corner detection, the differentiation technique behind them and all. What about curved borders, ma'am? If you have curved borders, how can you detect it?
Curved borders can also be detected using edge
Mm-hmm.
detection algorithms. Edge detection algorithms can be used to detect points wherever there is change border. Edge detection algorithms can be used there. But the edge detection algorithm, once we use it, it will be broken edges. We won't get the entire curve. So we have other techniques like Huff transform, etc., to fit the curves into these points. So those techniques can be used to get a proper curve.
And what about this kind of condola transform and all? I think they are also good, isn't it?
They are also good.
And we have to go in detail on them, and we have to try different methods and see, right, which is good
Yes.
and all, right? And ma'am, you have mentioned on databases. Is there any parameter or any way by which you can just check the authenticity of a database?
Usually what we do is we'll take the data sets from this prominent conferences, or if we need a prominent conferences, we have a backing from their end, so we'll have a good data set. And if we need the medical data sets, there are also in that case also there are some very prominent sites where you can get not just Kaggle or anything. But there are some very prominent groups that work on, that publish a lot of work on this. So you can look at the papers and decide what they have used. You can opt for data sets which were used by a lot of researchers. That will
Or
be it.
Yeah, and what about, if I just go and collect some data from maybe a renowned hospital, maybe if I'm working in medical image processing, will that be okay, or
It
should
will be okay, but
I?
the problem is you won't get quantity will be very low. That will be the problem which you will be facing. But
Yeah, yeah.
collecting data is always good in case of medical images.
And one challenge that I have personally felt is that you may get the data, but you may not be aware of what really the problem is.
Yes, that is another issue with collecting the data. The doctors won't have time to identify and give us the proper information regarding the data. So, to start with, it is better if you get some data from prominent papers or prominent authors.
All right, so that would be reliable. And still, many of us are still confused whether you have to go for the machine learning or the deep learning. What do you
Uh,
think on it, ma'am?
Machine learning, I have actually done my anomaly detection. I have researched on that.
Hmm.
I have used both machine learning and deep learning methods for anomaly detection. And
Okay,
machine learning, if you can find a proper feature,
okay,
it is always good to go with machine learning because it will have a good time will be very less. We'll require less resources. But deep learning, the accuracy is never comparable with machine learning. It will be very far better, but the resources require will be very high, and we won't be able to implement it in some hardware, or it won't be possible. So if properly engineered, a handcrafted feature with the machine learning algorithm would be good. But
yes. And let me tell you, if you're working, say, in mammogram, why people go with mammogram is that it's comparably cheap, right? So in those cases, it would be nice if you go with the ML, right? Because if you go with the, considering the cost and all, the cost of hardware implementation, if you go with the deep learning technique, implementing that would be a very costly affair, isn't it?
yes, it would be costly, and it you won't have resources available at your expense to do the things.
Hmm.
So it will be costly. But when you come to research side, you want to publish, right? But
Yes.
when you try to publish a feature extracted machine learning algorithm, it is very difficult. We have to really prove that our method is better than deep learning, and it should have a number of advantages. Otherwise, publishing side would be a bit difficult with the machine learning part.
Yeah, you meant that if you're working with those kind of the feature extraction method, the features that you extract should be really important, isn't it? You should not
Yes.
be taking something and just giving to a network, isn't it? What
You
you
have to mathematically explain why it is relevant to that particular application.
Yeah, that was really informative, Anitha, ma'am. Thanks a lot.
Okay, thank you. Any other questions?
Okay. Now I invite Sujit sir for presenting the virtual moment show and also for delivering the vote of thanks. Sujit sir.
Okay, miss. I, on behalf of all participants and Department of Electronics and Communication, College of Engineering, Perumal, I thank Dr. Anitha Edison ma'am for giving a valuable session on machine learning for computer vision. Thank you, ma'am, for spending your valuable time with us. I also wish to give her a virtual moment on behalf of you all for giving us a wonderful session.
Thank you.
Thanks, ma'am. Thanks. The lecture was so valuable.
Thank you, and good night, all of you. Can I leave?
Yes, ma'am. Thanks.
Thank you.
Okay, today's session is over. Tomorrow we can have case studies. from Jayaraj sir, NIT Calicut. Thank you.